Hello everyone, my name is Revan from CSM section C, and today I will be presenting my tech talk on Jordan echelon forms for linear state and input transformations. This topic comes to comes from the area of matrices and the calculus, which is deeply connected to control systems and linear algebra. My goal today is to help you understand what the Jordan echelon form is, why it's important, how it is derived, and how it simplifies the analysis of linear systems in state space form. By the end of this talk, you will understand how the mathematical transformation helps engineers design controllers, analyzes system behavior, and make complex problems much simpler. Now let's start with some introduction. Now let's begin by understanding the context. In control theory or system analysis, we often describe a physical system like a motor, robot, or electromagnetic circuit using state space representation. The general equation are x equal to ax plus b mu, y is equal to cx plus d mu. Here, x is the state vector which represents the internal condition of the system, like velocity, current, or position. U is the input applied to the system, such as force, voltage, or control signal. Y is output, which is what we measure or observe. A, B, C, D are matrices that define how the system behaves. However, when the system becomes large and the matrix A is complicated, analyzing the dynamics directly becomes very difficult. For example, if A has complex or repeated elegant values, it's hard to understand how system responds. That's where the Jordan echelon form helps. It provides a symmetrical way to simplify the matrix A into a structure that is much easier to interpret while still preserving all the essential dynamics of the system. We're going to the slide. What is Jordan echelon form? Now let's understand what Jordan echelon form actual means. A matrix is said to be Jordan conical form or Jordan echelon form if its diagonal, that is, the main diagonal contains small square blocks called Jordan blocks, and all elements outside these blocks are zero. Each Jordan block corresponds to an elegant value of matrix A. For example, J equal to 510, 050, 002. Here, the elegant values A and 2, the upper 2 into 2 block corresponds to lambda equal to 5. And the first 1 into 1 block corresponds to lambda equal to 2. This structure reveals how the system behaves in terms of natural modes or eigenvalues and their relationships. An interesting property is that Jordan form is unique up to the ordering of the blocks. That means no matter how you derive it, the structure will be the same. Only the order of blocks might change. We're going to next slide. Why Jordan form is useful. Now let's see why this concept is so powerful. The main purpose of converting a matrix into Jordan form it is to make the analysis of the system much easier. In the original state space, the variables may be mixed or coupled, meaning that a change in one variable might affect all others in complicated ways. But once it transforms the system into Jordan form, it becomes almost decoupled, meaning each part of the system can be studied independently. This helps in several ways. Solving differential equations becomes simpler because each Jordan block can be handled separately. Designing controllers like state feedback, or port placement becomes systematic since we know exactly how each elegant value affects the system. Analyzing controllability and observability becomes easier since the form exposes which parts of the system are independent or connected. In simple terms, the Jordan form acts like a magnifying glass. It reveals the hidden structure inside a complex system. Linear state transformation. Let's now talk about state transformation. Suppose we have the original state vector x and we define a new vector z related to it by x is equal to t capital T z, where T is transformation matrix that we construct using the eigen vectors and generalized eigen vectors of matrix A. When the substitute this into our original equation, x equal to ax plus b mu, we get tj dot equal to atz plus b mu. Multiplying both sides with the tree transpose T inverse, we obtain z star equal to t power minus 1 atz plus T inverse B mu. Here, T inverse A into T equal to J, which is the Jordan form of A. Now the system Z dot equal to JZ plus B hash mu, where B hash equal to T transpose B. This is new equation is simplified because J has a much more regular structure. Thus, the transformation from X to Z changes the system representation, but not its behavior. It just makes analysis easier. Input transformations. Input transformations. Next comes input transformation. The state vector, we can also adjust the input so that the entire system works neatly in the new coordinate space. This ensures that the question are compatible. We define a new input mu hash related to the original input mu as mu equal to r into mu hash, where r is the another transformation matrix. By choosing r properly, we can make the new input mu hash act directly on the simplified Jordan form system. This particularly useful when designing controllers because we can create control laws in the Jordan space that are the much simpler than then transform the back to the original space. So both state and input transformation are tools that allows us to reshape the system into a mathematical cleaner from without changing the actual dynamics. Steps to obtain example. Let's take a simple example to make this more concentrate. Consider the matrix A equal to 5, 4, 0, 5. The characteristic equation is A minus lambda A equal to where 5 minus lambda whole square equal to 0. So the elegant value is lambda equal to 5 with multiplicity 2. Now when we find integral vectors, we get only one independent integral vector. A minus 5i into V equal to 0, where V1 equal to I 1 comma 0. Because we need two vectors for 2 cross 2 matrix, we find or one generalized elegant vector V2 such that A minus 5i into V2 equal to V1. Solving gives V2 equal to 0, 1. Using these, we form transformation matrix T is equal to V1, V2, 1, 0, 0, 1. And compute J is equal to T transpose A into T equal to 5105. This is the Jordan form. Advantages of Jordan form. So, what we gain from this, from all this effort? The Jordan echelon form provides several key advantages. Simplification. It converts a coupled system into a simple and structured form. Clarity. It highlights elegant values, modes, and system behavior clarity. Control design. It makes designing controllers and observers more straightforward. Controllability and observability. It helps identify which part of the system can be controlled or observed. Analytical solutions. It simplifies solving the linear differential equations using matrix exponential. Now, summary and conclusion. To summarize today's presentation, we began with the linear state space representation and the challenges of the analyzing complex system. We introduced the concept of the Jordan echelon form, a block diagonal form from the simplified system matrices. We discussed state and input transformations that make system analysis easier. We went through the steps to compute the Jordan form and saw an example. Finally, we revived its advantages in control design and system analysis. Thank you for listening, and I hope you have a clear understanding of how Jordan form simplify complex systems into something elegant and manageable.